When it comes to volume procedurals, we also have to talk about one prime example that's really great to implement using volume procedurals. Fractals, like the Mandelbulb or the Julia bulb. So this is a general overview of how fractals like Mandelbulbs or Julia bulbs work, or also for a 2D case how the Mandelbrot or Julia fractals work. And regardless of the sometimes a bit daunting formulas that are involved, here is a high-level overview. So what we do to generate those fractals is we take point positions on a grid or in a volume. So they are usually denoted like this. It's a position consisting of an x, y, and a z component. And what we do is we plug these positions in some kind of formula. So here I have denoted my formula with a capital F, and that takes in variables such as the x, y, and z component, but also a variable called n. And n counts how many times we've executed this formula. This formula will spit out some result. And let's use this point here as an example point, and it's in the coordinates 1, 1, and 0. So we start by plugging in some values here. The x, y, and z component, and our n counts how many times we already executed this formula, and it starts with a 0. So this, in our example, will yield a result of 1.2. And f in our case is just a placeholder for something more intricate that we don't have to occupy ourselves with yet. So now we check if this result is bigger than some value. In our case, let's take 4. So we compare if the result of our formula is bigger than 4, and clearly 1.2 is not bigger than 4. So after we've checked if our result is bigger than 4, and we found out it isn't, we continue evaluating our formula. So this was our first run, clearly isn't bigger than 4, so we increase our n from 0 to 1, plug it in our formula again, and evaluate it with a result of 1.7. This too is not bigger than 4, so we keep on evaluating, increase our n by 1, it's now 2, results in a 2.4, and so on, till finally for an n value of 5, we get a result that is bigger than 4. So now that we finally have a result that is bigger than 4, we know we had to evaluate the function 6 times to arrive at this result, because our n is 5 now, and as we started with an n of 0, we had to evaluate this formula 6 times to arrive at a result that's bigger than 4. The final thing that we'll do is we color our point, whose point coordinates we use for this formula, depending on how often we had to calculate our formula to arrive at a result that was bigger than 4. And in our case, it was 6 times, resulting in an n value of 5. And what we do now is we check if this n value is, say, smaller than 6. And if it is smaller than 6, we color the point white, else we color it black. In essence, what we're doing here is we are evaluating how fast our formula goes to infinity for a given point. So when you think about it, the less iterations our formula needs to arrive at a given result, so the smaller n is, that means the faster the formula goes to infinity at this point. Basically, we are checking how quickly our formula is producing results over a certain threshold. And that is the essence, what both the Mandelbulb and the Julia bulb fractals do. Let's head over to Houdini and build this thing. So in Houdini, as always, I start by dropping down a geonode, diving in there, deleting the file, and creating a volume. In our case, let's call it density, and it should be 5 by 5 by 5 units big, and let's increase the sampling divisions to 100, so we have 100 by 100 by 100 voxels. And basically what I'm going to do now is I will implement a Julia bulb fractal, and all I need for that is one volume wrangle. And everything we'll do will go in here. So what I will need in here are 3 parameters that allow me to adjust the look of my Julia bulb. And I will call them offset, create a float slider to input that, hit create interface. I will need a float called n, and do not confuse this with the n in our previous example in the theory section, where the n was the counting variable that was used to count how many times I execute the formula. In our case, this is a variable that's intrinsic to the formulas that we're going to use, that basically will drive how many symmetry points the resulting Julia bulb will have, which I will show you in the end. So let's create a float slider for that as well. And also I'd like to be able to dial in the maximum number of iterations, so the maximum times that my formula will be evaluated. Let's use an integer for that, call it max iter for max iterations, and it will be an integer slider called max iterations. Let's, in our case, set the offset to 1.44. Let's start with, say, 3 symmetry points, and allow a maximum number of 16 iterations. Next, in our formulas, I will use 3 variables. And those are going to be floats, and they are called R, O, and P. Now, that's where the fun begins. And of course, I had to look up these formulas, and I will link to the website where I got them from. We start out by creating a vector called C. And to make this a bit more legible, I decided to calculate the vector's components individually. So let's call them Cx, Cy, and Cz. Let's create a float called Cx, and that is equal to 0.6 times the sine of 0.5 times our offset. Our Cy component will be 0.6 times the cosine of 0.784 times the offset minus 1.203. And our C component, Cz, will be equal to 0.6 times the sine of our offset times 0.439485. Pretty crazy, I know, and let's build a vector C out of these three components by using the set function to set its component to Zx, Cy, and Cz. Next, I'll create a vector called orbit, and that will store our current voxel position. So let's create a vector orbit and set it to our current voxel position, like so. Next, I want to create a variable that counts how many times we will evaluate the formula. So in our case, let's call this num, an integer called num, and with that, go into a for loop. So we'll create a for loop, and we will use our num, which we'll set to start at 0. We will allow it to run only up to our maximum iteration value, max iter, and we want to increase it by 1 each loop. Okay, now in the loop, what we're going to do is we will calculate a new value for our vector orbit and check if the resulting orbit vector is bigger than 4. And in order to calculate the new vector value for our orbit, we will need to calculate values for r, o, and p first. So let's start by calculating r, which will be the length of orbit. O will be the arc cosine of our orbit's z component divided by r, and p will be the arcus tangens 2 of our orbit's y component and our orbit's z component and our orbit's x component. Next, we will take r to the power of n, so r equals power function of r to n, and we will multiply o and p by n. Next, we will use RO and P to calculate our new orbit components, so x, y, and z values for orbit. So let's calculate our orbit x first, and it'll be r times the sine of O times the cosine of P. Our orbit's y value will be r times the sine of O times the sine of P. And finally, our orbit's z value will be r times the cosine of O. That's it for now. And finally, what we will do is we will add to our orbit vector, we're gonna add our C vector, like this. So let's check. No mistakes so far. That is cool. And now, after we've calculated all these values, and admittedly, these are some intricate formulas here that took a bunch of clever people a while to come up with. So after we've evaluated all those formulas, let us check if the length of our orbit vector is bigger than 4.0. And if it is so, we can break out of this loop here, so we can stop the loop. And after we exited the loop, either by calculating an orbit length that's bigger than 4, or just by running to the max iteration numbers, we will check how often we had to execute this loop. So we will check if our num variable is, say, bigger than 6. And if that's the case, let's set our volumes density to something really high, like for example 100,000. Okay, fingers crossed, and we can see we have this intricate structure here, which basically is our Julia bulb fractal. It's a good time to save this, and although we see a really interesting volumetric shape here, there are some issues with this, because currently our resolution is really low and our details are really low. So what happens when I crank this up to, say, a resolution of 500 times 500 times 500 voxels? Let's do that, and I will speed up what happens after I press enter. So this took some time to calculate, and admittedly now I can zoom in and have a closer look at this, but still there's not too many details. So again, let's increase this to, say, 2000 by 2000 by 2000 voxels. And again, I will speed this up. So that took somewhere between 2 minutes and 2 minutes 30 before it finally crashed. So we see giving this bit more resolution in the conventional way won't work for us. And this is a prime example of where volume procedurals come in extremely handy, because they allow you to basically generate infinite detail as long as you can put down a vex procedure that describes the volume's shapes. And luckily that's what we have in the volume wrangle. So let's dial back our volume resolution to something really low, like say 20, and create a volume procedural. So let's drop down a shopnet, dive in there, and in there we will drop down a vex volume procedural and a cvex shader builder. In the volume procedural, let's link up the cvex shader here. Also in the volume procedural, let's go to edit parameter interface, and in the render properties, search for IFD and drag the IFD bounds folder over there. Hit accept, so we can set it to use our subs bounding box and point it to our volume wrangle here. Hit accept, so that the bounding box of our volume is automatically set to whatever formula we put down in our original vex wrangle. Now let's dive into the cvex, and in here we're going to drop down a snippet, which we will configure to output density for our volume, and we will bind two parameters. On the one hand, the offset, and let's set that to 1.44. And on the other hand, we want to bind a parameter for our n value, which in our case, we're going to set to 3. Let's pipe those into a snippet. And in the snippet, let's configure the variable name 1, that's the offset, to be offset. So that's how we access it in the code here. And the n, let's set that to n. Now let's get up 2 levels and copy all this code from our volume wrangle that we just wrote, go back into our shopnet, into the cvex, and we will paste all this code in a snippet here. Now let's change some lines, so we don't need a float slider for our offset because we just directly pipe that in by the parameters. Same goes for the n. And let's not set our maximum iterations with a slider this time, but just set it to be fixed 16 iterations. And that should be it. So let's assign this volume wrangle on the geo level and up 1 level again. Here on our geo node, in the render section on the geometry tab, let's select our procedural shader, which is in the shopnet and which is this geo vex volume 1. Also, we're going to need some light. Let's put down an environment light here and a camera just by control clicking on those symbols. Also, let's close these tabs here, pin our current tab, hit Ctrl T, and in our second tab, let's open the output context, where we're going to drop down a mantra node, which we will set in the rendering tab to do physically based rendering. Finally, in our object level, on the environment light, let's assign an HDRI, for example, this one. Save this, and it's time to head to the render view. Let's just select our camera and hit render. And we can see, although we have a low volume resolution of 20 voxels, this already looks a bit more detailed, although not as detailed as I'd like it to be. And we can fix that in the output context on our mantra node. In the sampling tab, let's increase the volume step rate to, say, 2. And on the one hand, that takes a bit longer to render and to prepare. On the other hand, it generates lots more detail, as we can see here now. And for final rendering, I think I would set this to something like 8. Which of course takes a long time to render, but still is faster and more memory efficient than creating all this detail in our volume on the geo level. Just click on this area here so it converges a bit better, so we can see the detail that we're generating through this volume procedural here. Okay, let's stop this and head back to our scene view. And in our object level, I'd like to show you the effect of the n value that we talked about, and let's increase the volume resolution a bit so we can see it better. And let's look at this volume from the front here, and you can see now with an n number of 3 we have those 3 points of symmetry. You can see those 3 sides of our fractal really look similar, and by increasing our n value to say 4 we can dial up those points of symmetry. So we have now those 4 like corner points in our fractal volume, or even increase it further to 5, and you can generate a magnitude of very interesting shapes this way. Also, it would be a good way to link up these slider values into our volume procedural. So let's right click on the parameter, go to copy parameter, dive into our shopnet here, and in our VOP cvex, we can see those parameters exposed here. So let's right click on this and go to paste relative reference, go up again, do the same thing for our n value here, copy the parameter, and in the shopnet on the n slider, let's just paste it as a relative reference so it goes in sync with the settings that I have on my volume wrangle here. So my goal for this is not to be able to come up with those formulas for the fractals on your own. That's another universe of wonder and weird things. My goal is more to be able to understand from a high-level view what's going on when generating those fractals and being able to implement them, and being able to implement them efficiently using tools such as the volume wrangle in Houdini, which in this case is really the prime example of the power and what you can do with it. So I hope you had fun with this. As always, we are eager to see what you guys come up with, and see you in the next tutorial. Oh, and one more thing I forgot to mention. In the project file I also put in an OpenCL wrangle that generates a Julia bulb fractal for those of you interested in OpenCL and how you'd use that to generate those kinds of fractals. So have fun!